about this 2 by 2 matrix A, and then I'm asking you to compute A applied to these vectors. So it's very much like a linear algebra problem. So let me tell you why we're doing linear algebra. This is kind of the next sort of topic, the big topic that's going to take up a lot of time in the rest of the course. I think of this as this idea that everything is vectors. And to me, this is actually one of the biggest ideas in machine learning and data science, is that you can treat everything as a vector, and then by doing the right operations on the vectors, you can extract any kind of information you want. Okay? So let me give you some examples. Things that you've seen before that are vectors are things like information about a house, right? It has 81 entries. That's a vector of size 81. So this is called tabular data. That's what you guys have been doing, and this is a lot of classical data science stuff. It's tabular data, where every row is some kind of object, and you have entries. Of course, this is a vector. It's a vector of size 81. It's not that complicated to see, right? But other things like images like a picture of a cat. Let's try a picture of a cat. Here's my cat. That you can also think of as a vector. Or this one is the latest fashion in the last 2 years, is words or sentences, text, natural human text. You can also think of as a vector. So if somebody says the cat in the blank, you can use vectors to figure out what word would fit in this blank the best. You can ask what vector goes with the vector that goes with the cat in the. You can think of the cat in the as a vector. You can think of the blank as a vector. And you can say, what vector would fit in there the best? So you can think of all these things as vectors. So everything is vectors. And that is why we're starting with this linear algebra stuff. Because the very first thing we're doing is learning how the tools from linear algebra help you with vectors. And we're specifically going to learn linear algebra. We're going to learn, or we're going to remind ourselves of one trick, which hopefully you've seen in a good linear algebra class. Linear algebra has some big tools, some really nice theory, and one of the things linear algebra can do is it can help you condense vectors. You have like a big list of vectors, you can get into a short list of vectors. So we're going to learn condensing slash, maybe simplifying is the right way to do, using linear algebra, simplifying. And this idea is you have a big set of vectors or like a big matrix, and you're going to condense it down into something simpler. You're going to be able to think of complicated things in terms of less simpler things. So it's this idea of complicated to simple. So something that looks really complicated and difficult, if you apply linear algebra in the right way, will become simple. And we're going to make this more precise as we go. But all of these things, the images, the words, and so on, they have an obvious way. You can think about them as vectors. An image you can think of as a vector in r to the number of pixels. So you can think of every single pixel as its own vector element. But of course, this is ginormous. The number of pixels, even in a small image, is like 1,000 pixels. So this is a vector in r to the 1,000 just to represent a picture of a cat. Whereas actually, when you go online and you're looking at pictures of cats, there's like black cats and like gray cats and orange cats. There's not 1,000 different dimensions of cats. There's less than 1,000 dimensions. So how fat is the cat? How fluffy is the cat? So far we're up to 3. I'd be here all day to get to 1,000. So r to the number of pixels is huge. We want to condense down, and we want to condense down into r to the meaningful dimension. I shouldn't say mean. Let's call it the real dimension in quotes. So we want to. This number of pixel space is not actually very helpful, and it's the same thing with words. Every word can obviously be thought of a vector. You just take vectors in 0, 1, so either 0 or 1 valued, to the number of possible words. Right? So if there's 10,000 words in English, you can think of every single word as a vector which has zeros in every single entry except for a 1, 1 in the entry order. You can one-hot encode a word. So the word the would have zeros everywhere except for in the column, and it would have a 1. The word cat would have zeros everywhere except for in the cat column where it has 1. Of course, if you think of them like this, again, it's a huge space. The number of words is like 10,000. So you have these vectors of size 10,000. And worse yet, they have like nothing meaningful about them. The word cat and the word the are as far apart as the word cat and whatever word goes here, right? There's no relationship amongst the words. So you can think of things as obvious vectors by looking at the actual data, but it's not helpful for what you want to do. And so again, we're going to do this condensing idea, this condensing, simplifying idea. To condense down from the space of giant dimensions, we're going to condense down into a meaningful R to the real dimensions. We're going to convert words to vectors in some sense so that the actual vectors represent something more than just is it the or is it cat. Okay? And so we're starting with linear algebra, which is going to be kind of the simplest possible way to condense from complicated to simple. And then we're going to move to more complicated things, more machine learning type ways to do this complicated to simple thing. But always the idea is everything is a vector, and how can we take our data and write it as vectors that are meaningful so you can do things with the vectors. Any questions or comments about this idea? This is where we're going in the course for the next few weeks. So we're starting with this linear algebra stuff, which will be today's class and the class after that, but then it's going to continue with the same vector idea. Okay, so that being said, we're starting with a very dopey linear algebra problem, which could be a great linear algebra problem from a linear algebra class, about this 2 by 2 matrix. A is the 2 by 2 matrix 0, 1, 1, 1, and I'm asking you to please compute A applied to this vector 1, 1, and A squared applied to 1, 1, and A cubed applied to 1, 1, and so on. So this could be a very nice first year linear algebra problem. This is my favorite linear algebra problem that is an application of doing this condensing thing. So you're going to see there's going to be a complicated pattern in the answer. And by using the power of linear algebra, we're going to find a simple answer. We're going to find a nice simple formula that tells us the answer. So once you see what the pattern is and you do the problem, then you will know what it is. I see only 4 people have answered. So let me give you a few more minutes. Maybe you have to review how matrix multiplication works. You have to go find your note from first year linear algebra and see how it works. So let me give you guys a few more minutes on how it works. And there are a couple hints. One hint is that you can reuse each answer to help you calculate the next answer. So if you know the answer to A times 1, 1, then how does that help you compute A squared times 1, 1? Okay, you should be able to do it a little bit faster. And if you know A squared times 1, 1, you should be able to compute A cubed times 1, 1, and so on. And if you look at the numbers, there's a nice pattern that emerges. And you should, for example, A to the 4 times 1, 1. Okay, just like 10 seconds left. Hopefully you spotted the pattern, and you can continue the pattern to get the last ones if you haven't had time to compute them yet. Okay, let's take a look and see what people said. Reveal counts. 2 people said 0. 9 people said 1 in the top entry. So let's write it out and do it. This is the only way to do this problem, I guess. So we have the matrix 0, 1, 1, 1. that's A, and we're applying it to the vector 1, 1. What is this equal to? So you do 0 times 1, that's 0, plus 1 times 1, that's 1. So the top entry is a 1. So 9 people got that right. What about the next answer? The next answer, we're going to do 1 times 1, that's 1, plus 1 times 1, plus 1. So the next one is 1 plus 1. So the final answer should be 1, 2. 1, 2. Let's see how many people got 1, 2. 1, 2. 9 people. So 9 people are on board. 1, 2. What about the next one? Oh, well, an interesting thing I did is I made it so that this box and that box were the same. Why is this box and that box the same? Well, the row of the matrix, when you go to compute a squared, we computed a times 1, 1. When you go to do a squared times 1, 1, that will be a applied to a 1, 1, right? So we don't start from nothing. We take what we had before, 1, 2, and we apply a to it again. So this is 0, 1, 1, 1 applied to 1, 2. And when you do that, you have this 0, 1 like we had before, 0, 1 in the top here, 0 times the first entry, and then you get a 2 times the second entry, 2 times that, 2 times 1. So you always, whatever the last number is, will be the first number of the next one. The bottom number moves up and becomes the top number in the next answer, which was automatically done in mathematics. All right. Great. So very simple. For that top number, the numbers move up. What happens to the next number? 9 people got it right. It is 3. Why is it 3? Well, you have 1, 1, and just like before, 1, 1 is adding up 1 plus 2. So before it was 1 plus 1, now it's 1 plus 2. You're doing the sum of the two numbers. That's what 1, 1 means. 1, 1 means one copy of one number, one copy of the other number. Add them up. 1 plus 2, which is 3. So the answer is 2, 3. 2, 3. Let's do one more. What is a cubed? And again, you don't start from scratch. Don't try to compute the matrix a cubed. Take what you had before, apply a to it one more time. A cubed 1, 1 is a applied to the vector 2, 3. And maybe now you're seeing the pattern. You should be able to do this one quite quickly. What is it? You apply it. So the top number is 3. It always moves up. Top number is 3. Top number is 3. And the bottom number is what? Oh, only 7 people this time. Only 7 people got it right. It's 5. It's 5. Why is it 5? Because it's one copy of 2, 2, plus one copy of 3. Added together. Okay, so that's 3, 5. So the next one, let's try to do the next one without any matrices. Let's just look at the pattern. So we had 1, 1, and then 1, 1 became 1, 2, and then 1, 2 became 2, 3, and then 2, 3 became 3, 5. So the numbers always move up, right? 3 moves up, the 2 moved up, and then the other number also had a nice pattern. What is the pattern? What is the next one going to be, just based on the pattern?
It's the addition of both the elements.
It's the addition of the two elements. So the 5 will move up. The 5 will move up. The 5 will move up. And then you get 3 plus 5 equals 8. Very simple. Once you know this pattern, you can do this all day. The next one will be 8, 13. 5 plus 8 is 13. And the next one will be 13, 21. So we can do this all day long. Okay, let's see how many people got the one I asked you for. Right? The last one, the last entry. Ooh, it's a little split, so people were guessing. Only 6 people saw the pattern. So the pattern is, move it up, add them together, that gives you the new number. Move it up, add them together, that gives you the new number. Has anybody seen this sequence of numbers before? This is the Fibonacci sequence. So hopefully you've seen this before. Otherwise, you're in for a wild ride today. The Fibonacci sequence. So if it's your first time seeing it, congratulations on an exciting day. Every number is the sum of the previous two numbers. This is just the sequence. 1, 1, 2, 3, 5, 8, 13. Every number is the sum of the previous two numbers, 21. And it goes on forever and ever. And we did it by using linear algebra. So when you first see the Fibonacci sequence, you don't need any linear algebra. You just say, add them up. We did it automatically in the matrix. The matrix automatically encoded the rule. And actually, specifically, I'd say it's the bottom row of this matrix. The 1, 1 means add them up. Okay, great. What's the point of this? The whole point of this is I want to show you a cool example of this idea of complicated to simple. Right? This is what we're doing in data science. We're going to spend some time on it. And I want to show you the first cool example in linear algebra where you can do a superpower and you can take something that seems really complicated and turn it into something that is so simple that it takes 1 second to do, is a snap. And that problem is, what is the nth Fibonacci number? Here's the problem. And to make it concrete, let's say, what is the 1,000th Fibonacci number? So on this list, you're going to do it. You're going to do it 1,000 times. I want you to tell me the 1,000th number. And you might think, okay, this is a lot of work. You got to add up numbers all day long. Get out your calculator. Your buttons are going to be sore and red by the end of the day, typing in plus this, plus this, this, plus that. Another way to think about it is to do a to the 1,000. You got to do a times a times a times a times a 1,000 times. You got to do 1,000 matrix multiplications or 1,000 additions. And it seems like a lot of work. This seems like a hard problem. But actually, there is a sneaky, sneaky way where you can do this problem with no work, no matrix multiplications, not 1,000 matrix multiplications, 0 matrix multiplications. I can just give you a formula, and the formula is like the 1,000th Fibonacci number equals fib number equals, and there's a formula, and the formula looks like 2 to the power 1,000. Okay, it's not 2 to the power 1,000, but it's a formula that looks like 2 to the power 1,000. Okay? And that's what we're going to figure out right now. Using the power of linear algebra, we're going to figure out this magical formula. You guys with me so far? All right. So the question is, do you think you know what this magical superpower is? If you had a good linear algebra class, they showed you the magical superpower. If you had a medium linear algebra class, they showed you the magical superpower, but they made it so boring that you will not realize it's a magical superpower. You will think it's some kind of torture that they make you do. Okay? So the question is for you guys, do you know the trick to find the 1,000th entry? That's not what I want. Sneaky way. Here we go. So there, in linear algebra class, there's a sneaky way to compute a to the power 1,000 without having to multiply a lot of matrices. There's a nice exact formula for a to the power 1,000 for that matrix 0, 1, 0, 1, 1. This matrix, 0, 1, 1, 1. The sneaky way to calculate a to the n is to use blank. And if you had a great linear algebra class, you'll type it in. And if you had a medium linear algebra class, you'll say, what did I do in linear algebra class that was really painful? And you'll write down all the painful things you did. Okay, I'll give you guys a minute to think about that. Type in, what did you do in linear algebra class? Okay, 15 seconds left. You guys need more time to remember back to your linear algebra class. Okay, maybe I'll give another 30 seconds if people are still typing in how you do it. You can always put I don't know, very valid answer. You put I never took linear algebra, or I blocked all the memories of linear algebra from my brain. Okay, 10 seconds up. This time, put something in so I know where you are. If you put an I don't know, that's helpful for me to know. All right, let's take a look. Let's take a look. 9 people, I don't know. 1 person said recursive. One person gave me a formula, n minus 1 plus n minus 2. So I think both recursive and this formula are this idea of you calculate the 999th Fibonacci number and the 998th Fibonacci number, and then you can use those to get the 1000th Fibonacci number, right? The recursive is this idea, if you want to do something, first you do a simpler thing, and then if you want to do the simpler thing, first you do the other simpler thing. If you want to do the simpler thing, you do the other simpler thing, and then you're going to be there all day, right? So it's like, to find the 1000th Fibonacci number, I got to find the 999th. How am I going to find the 999th? It's the 998th. How am I going to find the 998th? I'm going to find the 997th. This is exactly what we want to avoid. Then we're going to be there all day finding all the Fibonacci numbers. And the sneaky trick that we're thinking of is we're trying to jump straight to the 1000th. Okay? No computing in between. We just straight up go for the 1000th number without computing the one before. So recursive is the sort of ordinary way. We want the sneaky way to do it. 9 people said, I don't know. Let's just yell out things you did in linear algebra class. What did you do in linear algebra class with matrices? That might be helpful. If you want to understand a matrix, how do you do it? Right? Because fundamentally, we're trying to calculate a to the power 1000. This matrix to the power 1000. And there is a matrix multiplication formula. You could multiply row by column like we did. But if you do that 1,000 times, that's what we want to avoid. So what else could we do to the matrix other than just multiply it out 1,000 times? Who took a linear algebra class? Okay, everybody took a linear. What did you do in linear algebra class? Did they just yell at you all day and then you did things? You're like, here you go. I don't know what we're doing. Name one thing you did in linear algebra class.
Using the determinant matrix.
The determinant. Okay, yes, this is great. So one thing we can compute is the determinant of A. And this is actually a useful thing because I'll tell you one thing. The determinant of a to the power 1000. We want to find a to the power 1000. I can tell you how to figure out the determinant of a to the power 1000. So I can't find the full matrix a to the power 1000, but I can tell you what the determinant of a to the power 1000 is in 1 second. And that is because if you took a good linear algebra class, the determinant of a to the power 1000 is equal to the determinant of a to the power 1000. Did you learn this in linear algebra? Hopefully you learned that. So we could do this. So we're looking for a matrix. I don't know what the matrix is going to be, but whatever it is, it's the determinant of a to the power 1000. The determinant of a is, what is the matrix A? A is 0, 1, 1, 1. The determinant is negative 1, right? You multiply these two, you subtract the other diagonal. So this is minus 1 to the power 1000. So good, we use the linear algebra fact to figure out the determinant of what we're looking for is 1. The determinant is 1. Okay, unfortunately, there are a lot of matrices whose determinant is 1, so we need a little bit more information. But this is a great start, the determinant. We got some information.
Eigenvalues and vectors.
Eigenvalues and vectors. Okay, what about eigenvalues and vectors? What are they, and how are they useful? Or did you just learn how to do it and stop there? Vectors. So what are the eigenvalues and vectors? It's okay if you can say, I just learned how to do it. I have no idea what it means.
I mean, it can use to calculate PCA.
Yeah, okay. You can calculate PCA. So you can use it to calculate PCA. Can you do anything else with it? I'll tell you one other thing you can do with it. You can calculate a to the power 1000. A to the power 1000. So if you do the eigenvectors and eigenvalues, and you know what the eigenvectors and eigenvalues mean, then it becomes super easy to calculate a to the power 1000. And I will tell you this, anytime someone says eigenvalues and eigenvectors, what they're secretly saying is, what would happen if the matrix was a diagonal matrix? Eigenvalues and eigenvectors are saying, we're going to look at the matrix in a different way. So instead of looking at it straight on, we look at it from over here. And if you look at it from the right angle, it becomes a diagonal matrix. So every nice matrix, if you look at it just right, it becomes a diagonal matrix. And just right means this giant word, eigenvalues and eigenvectors. But let's pretend the matrix A was diagonal. What happens if the matrix A was the matrix, I don't know, 2, 0, 0, 7? If A was diagonal, and I said, please compute a to the 1,000, right? All of a sudden, the problem becomes easy, right? Before, a was all mixed up. You had to do a whole bunch of this plus this plus this plus this. But if a is a diagonal matrix, 2, 0, 0, 7, how do you do a to the 1,000? Well, the 2 and the 7 are just completely in different universes. The 2 is multiplying by 2, the 7 is multiplying by 7, and they never talk to each other, right? So this thing in principle, a matrix like this A is all messy, mixes everything together. But if it's a diagonal matrix, then it's two easy problems, two separate problems that are both easy. So the matrix A to the 1,000 is just 2 to the 1,000, 0, 0, 7 to 1,000. Okay? So this is the whole point, is that diagonal matrices are super nice, right? Because they take something that is complicated, mixing up n different things, and they turn it into n simple problems. Here, it was 2 simple problems. What is the 2 doing? What is the 7 doing? And eigenvectors and eigenvalues are the idea that every matrix, or most matrices, not every single one, but most of the time, you can treat your matrix as a diagonal matrix as long as you look at it a little bit funny. Okay? And here is the way you can do it. There's a few different ways to think about it. But the matrix A, which is 0, 1, 1, 1, if you calculate the eigenvalues, so to calculate the eigenvalues, okay, and to calculate the eigenvalues, one way to do it is to use the determinant. So why are determinants useful? One reason is they're actually useful to calculate the eigenvalues. So I'll skip the calculation. I'll include a link if you want, and there's a note here where it's gone over in some detail. But the eigenvalues are two things: 1 plus the square root of 5 divided by 2, and 1 minus the square root of 5 divided by 2. So it comes out, you do a quadratic formula, one of the eigenvalues. Let's call that lambda. Actually, this number, normally you call the eigenvalues lambda, but this number, 1 plus square root of 5 divided by 2, already has a name. This is a famous number of all the world's most wanted numbers. 1 plus square root of 5 over 2 is like top 10. Does anybody know this number?
Golden number?
Yes, this is the golden ratio. Very good. This is the golden ratio. So we could call it lambda, but why would we call it lambda when it already has a beautiful name, and that name is phi, the golden ratio. Phi is the golden ratio. Does this number have a name? 1 minus square root of 5 divided by 2. No, it's like the golden ratio is like little brother who doesn't have a name. So sometimes people call it, it turns out it's equal to 1 over phi minus. So this number, I don't know why they decided to not give it a name, but it's the golden ratio's silly little brother, 1 minus square root of 5 divided by 2. Okay, so what does this mean? This means that the matrix 0, 1, 1, 1, the matrix A that we care about, if you look at it just right, and you've computed the eigenvalues, this matrix looks like the diagonal matrix 1 plus square root of 5 divided by 2, 0, 0, 1 minus square root of 5 divided by 2. Right? In some moral sense, this matrix 0, 1, 1, 1 is exactly the same as this other matrix. You just have to look at it in a different way. And what do I mean by looks like? I mean you have to work in a different basis. That's what it means. And this is all of linear algebra. If you had a good linear algebra course, they should have been telling you the whole time, all this eigenvector, eigenvalue stuff is just thinking of what looks like means. Probably in your linear algebra course, they didn't say any of that, and they just made you do formulas all day long, and you memorized a bunch of formulas, and then you went to the exam, and you regurgitated the formulas, and then you passed the exam, and you never thought about it again. But if it was a good linear algebra course, they would explain what looks like means. And looks like means you work in a different basis. So A is telling you what to do. If you know the first number plus the second number, it tells you what to do. You do 0 times the first number plus 1 times the second number. You do 1 times the first number plus 1 times the second number. That's what you guys did in the warm-up. But in a different basis, A looks like this matrix. And that basis are the eigenvectors. The eigenvectors. The eigenvectors. And the eigenvectors, again, when you calculate it, you can use determinants and solving linear systems, all of the like stuff they torture you with in linear algebra. It's not that it's useless, it's that it's useless unless you know where to use it. And you can use it right here. The eigenvectors are, so for 1 plus square root of 5 divided by 2, for phi, the eigenvectors are 1 phi, so 1 phi, this is an eigenvector. Let's call this V1. Let's call that V1. So v1 is 1, phi. And that means that a times v1, so if you do 0, 1, 1, 1 times 1 phi, then you get back phi times v1, 1 phi. So applying the matrix A to this eigenvector, it just multiplies by phi. And similarly, if you, for the eigenvector minus 1 over phi, 1 minus square root of 5 over 2, I believe it's, what is it, 1 minus phi? Let me see what it is. Let me not say it wrong. Yeah, okay, it's 1 minus 1 over phi. So if you multiply by this vector, you just get back this thing. Okay, so the eigenvectors have this nice property that when you multiply an eigenvector and you bump your screen, is it back? It's back, okay. So they have this property that a v2, let's call this v2, a v2 is also minus 1 over phi times v2. So when you multiply a by any vector, you get a big mix of everything. You have to add all the components in some funny way. But when you multiply by the eigenvectors, you just get the eigenvectors back. And what this means, by linear combinations, this is why this is the linear in linear algebra. If you add these two formulas, you can see that a applied to any linear combination, a v1 plus b v2 is equal to phi times a v1 plus minus 1 over phi times b v2. So when you do, if you express a vector as a linear combination of the two eigenvectors, then it comes out as a very nice linear combination of the two eigenvectors. And here's the thing, right? The a's and the b's don't mix. There's no a plus b over here. A becomes a, b becomes b. This is exactly saying that if you have a vector ab, it becomes phi times a minus 1 over phi times b, right? If you think of the linear combination ab1 plus bb2 as a vector ab, right? It's not literally the vector ab. It's like expressing the idea of a linear combination of two vectors. Then you're just multiplying each component. And that is exactly saying that this is becoming, you multiply by the diagonal matrix, minus 1 over phi, like times this, times AB. So what we're saying is if you work in the vector space, and you work in the basis, v1, v2. So don't think of vectors as being top number, second number. Think of vectors as being some number of v1s plus some number of v2s. And if you work in that basis, then it makes this statement, this looks like statement, becomes literally true. A looks like that. What do I mean by looks like? I mean, as long as you think of the vectors as being some combination of v1 and v2, then it's literally acting in the same way as this matrix. It multiplies however much v1 you have by this, it multiplies however much v2 you have by that. That's what it's doing. Okay, so if you take this, you can turn this into a statement, which is this statement. Okay, so two things. If you just know this idea, you can basically solve a problem. What is a to the 1,000? A to the 1,000. Like, morally speaking, it looks like phi 0, 0 minus 1 over phi to the 1,000, which is phi to the 1,000, 0, 0 minus 1 over phi to the 1,000. So the matrix A to the 1,000 will look like, this matrix. And one thing I want you to notice is that this matrix, we have it exactly, some number, 1 plus square root of 5 divided by 2 to the power 1,000. But not only that, this number, I claim, can even be simplified even more. What is minus 1 over phi to the power 1,000? Well, minus 1 over phi, it turns out if you put it on your calculator, is like negative 0.6, ... So what happens if you take a number like 0.6 to the power 1,000? It will become essentially 0. It will become essentially 0. This is approximately equal to phi to the 1,000. 0, 0, 0. The last entry over there is essentially a 0. And so what this is saying is that if you want to compute the 1,000th Fibonacci number, you're basically just going to be computing the golden ratio, 1 plus square root of 5 over 2 to the power 1,000. That's the only thing that's going to matter. And this idea of approximating, this is the essence of PCA and everything else that we're doing, of simplifying things. So this is the essence of PCA, which is that when you decompose things into their parts, some of the parts matter a lot, some of the parts matter a little bit. Let's only look at the parts that matter a lot. Okay? So in this problem, this simplification is just, this one doesn't matter. This is 0.6 to the power 1,000. This one is like 1.6 to the power 1,000. That's going to be a big number. That's going to be like billions and billions and billions. This number is like 0.0000. Doesn't matter. So this is the big idea. This is the essence of PCA and of this simplifying idea. And simplifying idea. And so we're using it here. So what this is saying is that the 1,000th Fibonacci number, so you want to do a to the 1,000, this is essentially, applied to 1, 1, this is essentially phi to the 1,000. Okay, except for, remember, to make it work, you can't look at the vectors inside their original representation 1, 1. You have to look at the representation as a linear combination of the two eigenvectors. So you have to do one little exercise, which is you have to write the vector 1, 1 as something times 1 phi plus something else times 1 minus 1 over phi. You have to write it in the right basis. So you have to make this looks like thing precise. Right? So we said it looks like this. So this vector looks like that vector, totally true. If we want to calculate this vector applied to some specific vector 1, 1, we have to say what does it mean by looks like. And it turns out that's right, there's a factor of 1 over square root of 5. So the solution to this problem is to put in 1 over square root of 5 for both coefficients. Let me just double check that that's correct. 1 over square root of 5. Yes, okay. Okay, no, I lied. One of them is 1 over square root of 5, and the other one is negative 1 over square root of 5. Okay, so one is 1 over square root of 5, and the other one is minus 1 over square root of 5. Is that possible? No, it's got to be a plus. Now I'm quite annoyed. Okay, I'm going to leave it as an exercise. You find the A and B. Find the A and B that work. The details are all here, but I don't want to say something that's wrong. So there's some A and B that work, and the answer will be this times A plus minus 1 over phi to the 1,000 times B. It'll be something like that. And at the end of the day, what you will get is that as a vector, the first component, the 1,000th Fibonacci number, which is the first component of A to the 1,000, that will be equal to this final formula, 1 over square root of 5 times 1 plus square root of 5 divided by 2 to the power of 1,000 minus 1 over square root of 5 times 1 minus square root of 5 divided by 2 to the power of 1,000. So this is phi to the power of 1,000, and this is phi's brother, minus 1 over phi to the power of 1,000. Okay. And the square root of 5's come from the solution. A and B involve square root of 5, which is where these things come from. So this is the final answer. And you can do it without ever multiplying any matrices. So you don't have to multiply 1,000 matrices. You just calculate the eigenvectors and eigenvalues, and you use that knowledge. So what you do is, like, every time you have to do a calculation of something, instead of working really hard and calculating it as is, you look at it the right way, which takes some work, and then it becomes dramatically simpler, and then you do all the work in the simpler space. So the huge speed up. So, if you have to calculate a to the power 3, like you guys did, not worth it. But if you want to calculate a to the power 1,000, definitely worth it. And like I said before, this term is approximately 0. So the actual answer is that the 1,000th Fibonacci number, up to some number of decimal places, is equal to 1 over square root of 5 times 1 plus square root of 5 over 2 to the power of 1,000. That's just the answer. No calculations needed. This is the 1,000th Fibonacci number. Okay, why am I showing you all this? This is my favorite, easy to understand example of the power of eigenvectors and eigenvalues. PCA is another application of eigenvectors and eigenvalues, and we're going to do that next. And that's very data science-y, and of course is related to data science. But hopefully this gave you a nice review of what eigenvectors and eigenvalues are, what they mean, and how they're useful. Because probably you did it, technically you did it in your linear algebra class, but you forgot or didn't remember why it's important. All right, this is a great place to stop if there's any questions or comments. Maybe I'll show you one last trick. Yeah, question here.
Some related task is depending on the pre-processing.
Uh-huh.
I want to know simplification for the data set.
That's right.
As you said,
That's right.
It's related to the pre-processing or is that just before the pre-processing?
Yeah, I think it's a type of pre-processing for sure. So where in the pre-processing pipeline you put it, that is up to you. I think the thing about this stuff, we're going to apply it, and you're going to see that really you take the data matrix, and that is some matrix, just the same way 0, 1, 1 was a matrix. And if you look at the data matrix as its eigenvectors and eigenvalues, it becomes simpler. That's the big idea. The same way we looked at the matrix A, it became simpler when we looked at the eigenvectors and eigenvalues. The way you do that is the eigenvectors and eigenvalues are linear combinations of the columns of A. And so once you start doing linear combinations of the columns, one thing you will lose is the meaning of each one. So if you have things from real life that you want to apply to your data, like people are typing in 117 years for how long they've had a driver's license, you want to deal with those before you do this PCA stuff. Because once you do PCA stuff, everything is all mixed together. So I think in terms of where in the pipeline it is, it's at the end of pre-processing, but after you do all of the things like delete stuff that doesn't make sense. And what it's going to do is it's going to combine all the information inside the matrix into more meaningful ways that are easier to understand what's going on. And so in the example I gave you, you had the matrix 0, 1, 1, and the eigenvectors and eigenvalues were these 1, 5, and 1 minus 1 over 5. Those are combinations of the rows. And it's going to be the same thing with PCA. I'm not sure. Did I answer your question?
Yeah, and one more question.
Yeah.
To me, this type of preprocessing is more related to knowing the business in close way, because for the other maybe preprocessing is maybe the general idea you can help
right.
to do the preprocessing. But for this such a simplification, I think you know to be more familiar with the related business you are working for. And I don't know, am I right?
Yeah, so I think this type of pre-processing is very mathematical, and you're saying I'm combining the columns in a way to get something that's mathematically nice. But it's true that it's harder to explain like what it is. So like when you say like I'm deleting this column because it's full of garbage data, like people typed in the wrong thing, perfectly makes sense to like a 4-year-old, right? Like people made a mistake, we're deleting it. This is like we're combining them in the special way to get a nice picture, and then say like, hey, what's special about the special way? And then you have to tell them, okay, well, do you remember in your linear algebra class where we had this thing that the a to the 1000 looks like this? So you start to get very mathematical. But you will see that it is capable of making nice pictures, and at the end of the day, what you can do to use it for is you can say, I took something that was 1000 dimensional, and I turned it into something that was 2-dimensional, and here's the picture of the 2-dimensional. So it's like keeping the essence of the 1000 dimensional thing and making it 2-dimensional. What is the best possible way to do that? It's this. And in the example we just saw, we took something that was 2-dimensional, 0, 1, 1, 1 is a 2-dimensional problem, and we turned it into a 1-dimensional one. At the end of the day, it only depended on this single number to the power 1000. And it really comes from throwing away, there were two things, there were two components, and one of them was smaller than the other one. And we said, let's only keep the big one. So that part of it is relatively easy to explain. You say, we had a 1000-dimensional thing, we threw it, we reorganized it in order from most important to least important, and we threw out the bottom 998 components. Here's the last two components, here's the plot. That makes sense. What are the actual two components? You're going to have to know linear algebra to understand what it is, which you guys will know, but like the business won't know. Yeah, fantastic comment. Anybody else for questions or comments? Okay, so let's see how this works. I'm going to show you now, we're going to have some data, and we're going to work with the data, and we're going to turn it into a linear algebra problem, just like this. And you're going to see that in the linear algebra problem, just like in this one, the solution was use eigenvectors and eigenvalues. The solution to the thing we want to do will also be eigenvectors and eigenvalues. So we're going to get to a linear algebra problem that's really hard, except for if you know eigenvectors and eigenvalues, it's like it's like easy. You just do it right away. And here is the problem. So we have this data, and let me turn off some of these things. Let's just start with just the data. So here is some green data points. Are they? Okay, yeah. So here's the green data points. And here is roughly the idea we want to do. We have this green data, which is 2-dimensional data. There's an x and a y, or an x1 and an x2, and we want to somehow condense it down to 1 dimension. And if you look at the picture, it's very obvious that there is a direction that they're mostly spreading out, which is this 45-degree line, right? If I want to describe this point over here, I really don't need two numbers to tell you this point. So So very strictly speaking, this is the point 5.1, 6.1. But I could also just say, look, it's like along the line 5 units from the origin. Just go diagonally upward for 5 units, that's the point I'm talking about. And of course that's not perfect, because it's not exactly on the diagonal line, but it is pretty close. So I can sort of distill this 2-dimensional data set, I could distill it down to 1 dimension with kind of a minimal loss of information, right? So all of these points, even though they're strictly speaking 2-dimensional, we could think about describing them 1-dimensionally if only we knew the equation for this line. So how are we going to do that? We're going to find the equation for this line. So what we're going to do is we're going to think of working in a different basis. So we're going to pick a line like this, and we're going to project the data points onto the line. So, and I've drawn this little green thing. This is the perpendicular projection. We're taking the original green data point, and we project it onto the line by drawing a 90-degree angle and projecting downwards. If you took a good linear algebra class, you know that to compute the projection, you do the inner product. So this blue line is some vector. You do the inner product of the green dot with the blue line that tells you where it projects. And so I've done this original data point over here, this like sample test point, but I've also done all the other points. So you can see, if you do it like this, you just get the x1 coordinate, right? So that point gets projected down to here, and so on. That'll be 5.1, and so on. And that'll be close to 0. That'll be some negative number over here, and so on. If you do it at 90 degrees the other way, you get all the other points. You get the x2 values. So if you have it perfectly flat, you get the x1 values. If you have it perfectly the other way, you get the x2 values. If you have it somewhere in between, you get exactly what I was saying before. Probably we want a line like this, where we're going to replace the original green data with the blue dots, and they're pretty close. Okay. And the problem is, mathematically, the problem we have is, which line should we pick? Like, we don't want to just eyeball it every time. We want a mathematical way to come up with the best possible line. So you can pick any direction. It could be anywhere around here. It could be any line in the world. And we need some way to say what is the best possible line. We need a criteria that we can use. So that is the mathematized question. What is the best way? To pick the best direction, here are 2 options. We should make the projection of the points as spread out as possible, or we should make the projection of the points as close together as possible. And what do you think is right? So that's open. You can visualize playing with this, or you can open the link and do it. I believe there is if you go to the GitHub, there is a link in the PCA folder that has this. Okay, so you just imagine, use your imagination, or you could really do it. Do we want to spread them out, or do we want to keep them close together? Okay, let me start the timer here for 30 more seconds. While you think about which would be better for what we want to do. Okay, let's take a look at what you guys said. Do we want to spread the points out or put them all, bunch them up? Ooh, even split. Very exciting, guys. Good work. So, at a 50-50 split, let me show you the picture of the 2 options. So right now we're somewhere in between. If you want to spread them out, you would do something like this. Look at, they're all spread out, right? So we're looking at the blue dots, right? The green dots are fixed. We're not messing with the green dots. The blue dots are the projection of the green dots. This way they are all spread out as far as possible. And this would be, they're all bunched together. Look at that. So you see how all of them are, when you do it this way, all of them are really tightly in there. So we're talking about on the blue line, how far spread out are they? And which do you think is a better summary of the data? Is it the points like this, the blue points here, or is it the points like that where they're spread out? So I'll let you revote. 7 to 6, feel free to chat with your neighbor about what it is. Now that you've seen both options. Okay, best direction V2, it's open. All right, 10 seconds left for the last two people. Put in what you think now that you've seen it. Okay, let's take a look. Make it as spread out as possible, 12 to 0. Amazing, amazing change. That is the correct answer. So very well done, everyone who switched. So when you spread them out like this, you see, because they're so spread out, what is left over is a very small amount, right? They're really spread out this way. And by spreading them out, you can tell the difference between the points. Like, you're never going to mix up this point with that point. They're so far apart, right? Whereas if you bunch them all together, if you did the opposite, then all the points would be mixed up, right? You wouldn't know the difference between this point and that point, which is not what you want. So you want to spread them out as much as possible. So now the question is, how can you measure how spread out something is? Did I bump the thing again? Okay. So we need a number that describes how far apart points are. I give you a bunch of points. I want you to do some calculation and tell me the number that tells me how far apart they are. Anyone have any ideas? We've done a bunch like that. Yeah.
We calculate the eigenvector of covariance matrix.
Uh-huh.
And the eigenvector
Yes.
with highest value of
Yeah.
eigenvalue
Yeah.
is chosen as the first component.
Yes. So you're telling me what the answer is going to be, right? You're saying the blue direction you should choose, it's going to turn out exactly like you said. The blue direction, the best possible direction, the one that spreads things out the most, will be the top eigenvector. So it will turn out that the blue direction is the top eigenvector. But I'm asking, what is the question, right? So you're telling me the answer. I'm trying to figure out what is the question. And so the question is, we want to spread it out the most. Spreading it out the most means maximizing some number. What number is that? And if you pick the right thing, you do get the eigenvector. How do you measure how spread apart points are? I give you some points over here. I give you some points over here. Which one's more spread apart? Calculate what?
The covariance.
The covariance. Yeah. So the covariance, remember, variance, like we learned, is like a square thing, right? You take the things, you square them. So the variance will have units of distance squared. And if you take the root, then you get the root. It's like the root mean squared error, but it's not an error, right? It's just the root mean squared distance from 0. So the variance is like the squared distance from 0, and the root mean squared is the root of that. So that is what I calculated, and I think I called it the sum of squares, the score. The score. And this is the sum of squares, except it's the root sum of squares, I believe. Yeah, so it's the square root. You take all the distances, so the distances on the blue line, how far are you from the origin? Square them all up, that's like calculating the variance, and then take the square root. So this is like the root mean sum of squares. And that is a number that can either be higher or lower. So if you put it like this, it's a very low number. All of the things are bunched up here. They're typically only 0.6 units from the origin. If you do it like this, if you do it perfectly like this, then that is exactly the x1 data. That would be like the variance of just the column x1. And if you do it like this, it would be like the square root of the variance of just the column x2, which is a little bit higher. And we want it to be, we said we want it to be as spread out as possible. Let's make this number as big as possible. We will just turn the line until we find the maximum. And I think the maximum, it's going up for a while, 4.65, 4.651, and then it starts to go down again. So down, up, down. So the maximum is somewhere here, like that. There's the maximum. So now we have a perfectly good defined procedure to find the best possible blue line. And we're going to take our data and project it onto this blue line. And really projecting it is thinking in a different basis, right? Instead of thinking in terms of x1 and x2, we're thinking of how far along the blue line are you? And once we know how far along the blue line you are, we can take any other data and like work perpendicular to that. So we say how far along the blue line you are, how far are you perpendicular to the blue line? That'll be the component 2. And we want to maximize this thing. And it's going to turn out that the way to maximize this is the top eigenvector. Let's see why that is. So I'm going to show you mathematically where does this eigenvector thing come from. It's not magic. It's exactly the kind of thing we were doing a second ago. So here is the setup for PCA. PCA setup. Let me zoom out one. Okay. Okay. So the setup is we have our data. I'm going to put all of our data in a big matrix X. So X is going to be a matrix. This is the data matrix. The data matrix. And so it's going to be an n by p matrix. So I'm going to draw it like this. I'm going to think of the rows as being the vectors x1, x2, all the way up to xn. And each one is a vector, is a row vector, which is p units 1. So it's p rows, or sorry, n rows, where n is the number of data points, number of data. And it's p columns, where p equals dimension of data. And so in our example, p equals 2. We're doing the 2-dimensional example. So in our dimension, in our example, we had, I don't know how many points we had. How many points did we have? Someone tell me. Data. We had 11 points, and they're each in 2 dimensions. There's an x1 and x2, so it's a long matrix with 11 rows and 2 columns, right? So just like you see when you do pandas or whatever tabular data, we have this thing. Okay, and what we're going to do is we're going to try to find the direction of that blue line. Okay, and that blue line is a vector, which is a 2-dimensional vector. So it's going to be some vector. I think I called it W, and in fact I called it W1, and that's because what we're doing is we're finding the best direction, and you can also find the second best direction, and so on. But right now, let's just do just the best direction. We'll do one direction at a time. So W1 is going to be a vector. It's in R to the P. And this is the blue line. So the example is it's the blue line direction. So in our example, you might say that W1 is just the vector 1.97, 1.992. Right? That would be the vector. So just what direction is the blue line going? And if you know the direction of the blue line, you can calculate where are these points. The projection of the green data onto the blue line are given by inner products. So if you choose, once you've chosen a direction W1, you can get all the points you want by doing inner products. So you're going to do inner product. So the projected data. So originally the data was in the matrix X. Which was, so this is original. Let me just do it like this. So we're going to do x1 with w1, and these are vectors. So we're doing a vector inner product. I'm using this notation of curly angle brackets for an inner product. You might have seen it with a dot for a dot product. I'm doing it this way. So we're doing this all the way up to x times n with w1. And so this is a vector of numbers, right? If you take the inner product of the vector x1 with w1, that's 2 vectors, and you're just saying like how much they point in the same direction. That is some number. These numbers tell you how far you are along the blue line. So in fact, I think I put it in Desmos. If you calculate the dot product, these are exactly the formulas for the dot product. Let's turn this one off. So the numbers, right? They're numbers. But if you think of them as how far you are along the blue line, that's exactly what we want. So these are the numbers that tell you how far you are along. And I will point out that this is the whole point. This is the matrix vector multiplication of x times w1. X times w1. So w1 is a 2 by 1 vector, and x is an n by 2 matrix. So you can do it n by 2 matrix times a 2 by 1 vector. You get an n by 1 vector. That's how far you are everywhere. And you guys said we want to make the projected data as far apart as possible. So let's call this P for projected. I guess P is already taken. Let's call it R for projected. So this is this R vector. And you said let's spread out R as much as possible. So we want to maximize the distance squared of R. So just make this R vector, spread them out as much as possible, make that vector have, if you add up the sum of the squares, as big as you can. And your choice, you get to choose the direction W1, right? Your choice is to choose W1. So you're maximizing W1. You get to choose the vector W1, and you want to do it in such a way that they're spread out as much as possible. And we have a nice formula now, because this is the maximum of W1 in R2. So choose the best vector R, and R was the matrix X hitting the vector W1. So you want to find the vector W1, so that when you do X W1 and you take the norm squared, it's as big as possible. Now the norm squared, there's a nice way to write the norm squared, which is the inner product with itself. W1 in R2. That is the norm of X W1 with X W1. That's what the norm squared is. It's the inner product with itself. And this is, again, if you had a good linear algebra class, you will know exactly how to handle this. If you had a medium linear algebra class, they will have tortured you with a bunch of rules, but not explained where they come from. So maybe your rules brain will kick in here. If you have XW with XW, what can you write that as? You can write it as XW transpose, so this T stands for transpose, times XW1. So doing the inner product is the same as taking the transpose. And now, doing the transpose of a matrix vector multiplication, x times w, and then do the transpose, that's the same as doing the transposes and multiplying, but in the reverse order. So this is, again, from a linear algebra class. You learn all these rules. That's why they torture you with linear algebra, to make you do these kinds of things. Okay, so it's w1 transpose times x transpose times x times w1. And this is where the key thing happens. By doing this, all this stuff, we've gone away from the matrix X on its own, and now we're looking not at the matrix X, but the matrix X transpose X. And we've seen this matrix before, the matrix X transpose X. That came up when we were doing linear regression too. Let's write down what is the matrix X transpose X. So X is a n by p matrix, n data points. I'll do 2. This is the data dimension, just to keep things concrete. So X is n by 2. X transpose, when you transpose it, it becomes a 2 by n, right? It's a two data dimensions by n data points, data size. Let's say points, because size, I guess, could mean dimension as well. Points, the number of data points. So when you do this, you're adding up over these n data points. And so really what this is, the ij entry of this is the sum of xi, or let's do it like this, xki with xkj summed over the data points, and data. This is the number sum over all data points. So it's saying you take direction I, you take direction j, and you see how much do they overlap. How much do directions I and j overlap? So this thing is called, this is exactly the covariance. This is the covariance of feature I with feature j. Feature I and feature j. So this matrix is sometimes called the empirical covariance matrix. This thing is called the empirical Okay, so it's the covariance matrix because the entries are the covariance. What's empirical about it? Empirical just means using the data set, adding up over the data set. not like the true, there's a true covariance matrix. We don't have access to that. We only can see the empirical one. Okay, so now we have this problem of you have the empirical covariance matrix. Please find the direction W that makes this number as big as possible. And this is exactly the kind of algebra problem that seems really, really hard. Just like calculating 8 to the 1000, you're going to calculate this matrix X transpose X. It's going to be a big mess. It's going to have lots of numbers all over. What direction? How do I make this as big as possible? So X transpose X is some weird matrix. Which way makes it as large as possible? So it's a hard problem. But I'll tell you, there's one special case where it's a very easy problem. Let's pretend X transpose X. Let's go with our favorite example. Let's pretend X transpose X was the matrix 2, 0, 0, 7. Okay? And someone says, I want you to find W. So W transpose X transpose X. W is maximized. And in this case, because X transpose X is such a nice diagonal matrix, when you write out W transpose X, W, it's a very simple calculation. It's going to be 2 times W1 squared plus 7 times W2 squared. That's what it's going to be. And there's no terms of W1, W2 because there's no entries. It's 0 there. So when X transpose X is a diagonal matrix, it's a very simple thing. How do you make 2W1 squared plus W2 squared as large as possible? Well, you just make W1 0 and W2 1, right? You have 2 times this thing squared plus this times this thing squared. It's like you can buy apples for $2 and you can buy sheep for $7. I don't know, apples and sheep. How do you make it the most? How do you make it as large as possible? Don't buy any of the $2 ones. Buy all the $7 ones, right? You want to make it as big as possible. Put all of your bananas in this category. Okay, we got bananas, apples, and sheep. Okay, so if it's a diagonal matrix, the solution is obvious, which is choose W1 equals 0 and W2 equals 1. That's the obvious answer. So that's the vector 0, 1. So when it's a diagonal matrix, it's a really simple problem. In general, it's a very complicated problem. It's a really hard problem. How do you maximize this? But if it's a diagonal matrix, it's trivial. Just pick the biggest number of all the numbers on the diagonal, pick the biggest number, put everything in that direction, ignore everything else. And now is the miracle of linear algebra, just like we saw with the Fibonacci numbers. It's not true that every matrix is a diagonal matrix, but every matrix, if you look at it from the right point of view, if you change the basis you're working in, instead of working in 0, 1, 1, 1, you look at the eigenvectors and eigenvalues, every matrix becomes diagonal. So if you look at the matrix X transpose X and do its eigenvectors and eigenvalues, what this is saying is the solution is the largest eigenvector. So the solution to this problem, in general, when it's diagonal, it's obvious, and when it's not diagonal, you make it diagonal in the eigenvector basis, and the solution is the largest eigenvector. In general, W transpose X, W is maximized when W equals, I'm going to call it V maximum, and that's the eigenvector that goes with lambda maximum, the largest eigenvalue. Okay. So that's the answer. The answer is, and again, it's the power of linear algebra, which is that very difficult problem, but it's easy for diagonal matrices, and you can convert it to diagonal matrices by just looking at eigenvectors and eigenvalues. So every matrix looks like a matrix of the form 2, 0, 0, 7, as long as you look at it in the right way. And looking at it in the right way means think of the eigenvectors and eigenvalues. So in this particular example, the largest eigenvector of the data matrix, of the empirical covariance matrix for this data is exactly this direction. That's the largest eigenvector. And it turns out you can prove all the eigenvectors will be perpendicular to each other because it's a symmetric matrix. So that's the largest eigenvector. The next eigenvector will be the perpendicular direction over there. And in general, you have this whole sequence of all the eigenvectors, and if you sort them from largest to smallest, they sort of tell you which directions matter the most, right? In the top direction, it's the most spread out. In the second most direction, it's perpendicular to this direction. It's the next most spread out. In 3 dimensions, you have a third direction, where it's the third most spread out, and so on, going from most spread out to least spread out. And most spread out we think is good, is sort of representing the data as well as possible. Least spread out we think is not important. right? We think this direction is really important, and the perpendicular direction like this, that direction doesn't matter. Because in this direction, it doesn't matter. All the points look the same. They're almost the same. We don't care about that. We just delete that from your memory. It doesn't change anything meaningful. So that's the idea. We're looking at from largest eigenvector to smallest eigenvector to get the idea. Okay, so now you've seen all the math. Any questions or comments about any of the math? So again, there's a lot of details from linear algebra I'm skipping over, like how do you find the eigenvectors and eigenvalues. You guys probably don't need to worry about that. You can just call the function, find the eigenvectors and eigenvalues, but you should at least know what it's doing. And that's why I'm explaining it all to you. And that's also why you would never do this in a company, right? In a company, you would just say, like, how do we sell more cars or whatever? So this is your chance to learn how it actually works under the hood. Questions, comments? Okay, so next class, we're going to do a whole bunch of different examples and like real life examples. So I have a couple of different data sets. There is also NumPy in Python, the Python notebook, that does the same thing we did in the Desmos, but in Python. So I can walk you through that quickly here, and then you can look at it on your own. So here is the data. So it should look very similar to the data in Desmos. So those are the blue dots. And then we calculate, this is a function which is the norm of xw squared. The norm of xw squared as a function of where you are. So if you pick the vector w, which is over here, you get a certain norm of xw squared. And that surface represents the values. And that's what we're trying to maximize. In our problem, we were trying to maximize the norm of xw squared, right? That was this thing. And so you can see that from this notebook, you can see that the directions where it's maximized, those are the directions here are the eigenvectors. The direction where it's maximized is by going up the hill as steep as possible, is going this way. And this way is a very wide valley again. So it's very similar to what we saw. It's exactly the same linear algebra concept as we saw before with the multicollinearity. And so in this case, you want to make it as big as possible. You pick the largest eigenvector, which is this way, and the next eigenvector is that way. And so those orange arrows tell you the eigenvectors, and they are computed with this function np.linealg.eigh. And look, I did it on the matrix x transpose x. So you can see exactly how it's done in a very hands-on way. And last but not least, what you can do is you can transform the points. So the points before you could think of as having an x1 component and an x2 component. And then after you've decided what w1 is, instead of using those coordinates, you use these transform coordinates. So I wrote them down here. These are the transform coordinates. You do the inner product with the vector you found. So you found the vector, and then you transform the coordinates. And now it looks like this. So here is the transform data. And the x1 is chosen to be as spread out as possible. I guess it's this way. How do I do this? Is the scale funny? Well, okay, they're maximally spread out in one direction. So it's sort of taken the whole thing, and instead of having the x1 and the x2 are related, now they're sort of like unrelated as much as possible, right? They're mostly spread out in one direction, and they're less spread out in the other way. So this idea of transforming the points, once you've found the optimal directions, you just take the inner products, and that transforms them, and you get, from the original data set, you get a new data set, which has the exact same information, but is transformed. And then you can apply the very last step, which is what we did in the Fibonacci numbers as well, which is you can delete the ones that are unimportant. So in this case, it's more spread out in this way. You can delete everything except for how it's spread out in that way. So you can take your data set, which is now two-dimensional and transformed, but it's transformed in such a way that the different axes you have, you can just delete the least important ones. So you keep the most important one, delete the least important one, and hopefully that will tell you any questions you want about the data will be all contained in just that most important vector. So you've effectively gone from a two-dimensional problem to a one-dimensional problem. Okay, and we're going to see lots of examples with that next class. So there's some that are mathematical, and then there's some that will be like real-life problems. So this is one we're going to get to next class. So these are some different countries, and we're going to compare them using PCA. That'll all be next time. Okay. So we'll stop there. See you guys on Tuesday. Don't forget to submit the draft of your project by Sunday. and partners if you haven't done that yet. Okay, take care. Have a fun weekend.